Greetings and welcome to the complete lecture for Chapter 6 of Chemistry 221, which is called The Composition of Substances and Solutions. And we're going to see here that there's a lot of utility that a chemist can get out of a solution. And knowing about the composition of different things can certainly help a chemist as well. And you can see the poor cave people there that are trying to determine the formula for the dirt molecule. Oh, I have a strange sense of humor. It cracks me up. But without any further ado, let's check out this chapter and see what it has to offer. In this chapter, we'll talk about formula mass. And the formula mass, which is used a lot for covalent molecules, is just the sum of the average atomic masses of the atoms in the substance's formula. And basically, the formula mass is also equal to the molar mass, which we saw earlier, the grams per mole in a molecule. So for covalent molecules with non-metal compounds, the formula mass is literally just the mass of the molecule. No big deal. Here's an example of chloroform. Chloroform is CHCl3, and the molecular mass, which is the mass of an individual molecule, is the same number as the molar mass, which is the grams per mole when you have a mole of things, which is what chemists usually use. And to figure this out, you'd have 1 carbon, 1 hydrogen, and 3 chlorines. And those values there are listed to the hundredths on the periodic table, which are great for most of the time. When you add them all up together, it's 119.37 grams per mole. So we would call 119.37 grams per mole the molar mass of the compound, and that's also equal to the formula mass because CHCl3 comes in individual molecules, so the formula is 119.37. And again, that number is pretty cool because it represents the average mass of one molecule, if it's AMU, which is very, very small amounts of grams. But what's more useful to chemists is the molar mass, which is grams per mole. That's the grams in a mole of the compound. So in a mole, you have 6.022 times 10 to the 23rd molecules. So the number is the same. If you change the units, you can have a molecule's mass or a mass of grams in a mole of the substance. They're both really cool. For ionic substances, though, it's a little bit different. In an ionic compound, you don't really have discrete molecules, but you do have smallest units that repeat each other over and over again to have like an empirical formula, if you will. So for sodium chloride, in the lower right-hand corner, that kind of cubic thing, that's really what happens when you have sodium and chlorines next to each other. It's not an individual sodium and an individual chlorine, but it's repeating NaCl, NaCl, NaCl. And it's all 3 dimensions, up, right, left, forward, back, all those different ways. So chemists refer to the formula mass of sodium chloride as having 1 Na and 1 Cl, and that's the molar mass. Now, honestly, this is kind of a nitpicky thing that we're not going to worry about too much, but just realize that with ionic compounds, you've got lots and lots of them kind of smashed together. And when we find the molar mass, it's really the mass of one formula unit. It's like 1 Na and 1 Cl. But in reality, you have a whole bunch of them going on, but all the rules still apply and no problem. So if you can find molar mass for a compound, you're good to go, whether it's covalent or, in this case, ionic. So this next step is arguably one of the most important parts that we've looked at so far because it's really going to discuss how chemists determine what a chemical is. So imagine, for example, that one of your grandparents hands you a chemical and they're like, what is this? And is this safe to drink or whatever? And you're like, oh man, don't do that. So you've got to find out what it is, and you don't want to drink it and you don't want to smell it because there's a lot of really deadly things out there. So what a chemist will usually do is they'll take the chemical and they'll send a little bit of it off for analysis. And the analysis, the goal is to get what's called the molecular formula. The molecular formula is kind of the holy grail of this kind of stuff. And if you have the molecular formula, then you can figure out what it is. But in the process of determining the molecular formula, a lot of times the chemist will have to go through what's called the empirical formula. And the empirical formula is the smallest whole number ratio of atoms in the formula. So on the little table there in the middle right, you can see the comparison of molecular formula versus empirical formula. Now, it's really important in the empirical formula to have the smallest whole number ratio. Chemists don't do fractions generally, and we're certainly not doing fractions in this section. So H2O, for example, which is water, the empirical formula, the smallest whole number ratio of atoms would also be H2O. Now, yes, you could have an empirical formula of H1O.5, 1/2, but don't do fractions in my class, especially not right now. So H2O is the empirical and the molecular formula. So let's look at some more exciting examples. Glucose is a type of sugar. The molecular formula is C6H12O6. Well, the empirical formula, the smallest whole number ratio of atoms, if you divide the 6, the 12, and the 6 in the formula, divide them all by 6, you get C1H2O1, or CH2O is the empirical formula. And again, don't go to fractions, smallest whole number ratios. Likewise, hydrogen peroxide, H2O2 is HO, butane C4H10, which is used in cigarette lighters, by the way, would be C2H5, etc., etc. If a chemist has the empirical formula, they can use a mass spectrometer, which we talked about in chapter 2, to find the molar mass of the compound. And between the molar mass of the compound and the empirical formula, you can find the desired molecular formula. So we're going to explore this whole pattern, this pathway, in this section, and I'll show you how chemists do it. One of the types of analysis that chemists will send away these unknown chemicals for is called a percent composition. And there's various ways to do a percent composition or percentage by mass analysis. Atomic absorption is one method, but there are several of them. Anyway, you'll end up then with these percentages of the elements in the compound. So in the bottom down there is an example of ethanol. Ethanol has a molecular formula of C2H6O, and you can see that that compound is 52.13% carbon, 13.15% hydrogen, and 34.72% oxygen. Now, eventually, we're going to take those percentages and turn them into empirical formulas, but we should also talk about a little bit about how these compounds came to be. But before we do that, all of your percentages for the elements should be very, very close to, if not equal to, 100%, because these are all the chemicals in the compound. So these percent compositions will tell you what kinds of elements you have. So for example, ethanol has carbon, hydrogen, oxygen, but no nitrogen, no uranium, stuff like that. And it will lead to an empirical formula, but it doesn't lead to that molecular formula. So now first, before we talk about how to get to molecular formula, let's see how percent composition can help us, and also how to calculate what the percent composition should be. This is an example where we have 10 grams of some compound, and it's found to be 2.5 grams hydrogen and 7.5 grams of carbon. We can find the percentage by mass of hydrogen and carbon using this information. And it's probably not too hard, and maybe you can figure out how to do this, but if you can't, no big deal. These percentages, what you want to do is take the grams of the good stuff in the numerator, the top, and divide by the total mass of whatever you're looking at in the bottom, and then multiply by 100%. So for hydrogen, that would be 2.5 grams of hydrogen, the thing we're looking at. We'll divide it by the total mass, which is 10 grams, multiply it by 100%, and this comes out to be 25% hydrogen. So our compound is apparently 25% hydrogen. Now, to find the percent carbon, which is the other thing, there's two ways you could do it. You could take 7.5 grams of carbon, which is how much was found, divide it by the total 10 grams, times 100%, 75%. That's legit. But you could have also found it remembering that all of the element percentages together equal 100%. So 100% minus 25% hydrogen would mean you'd have to have 75% carbon. That's a nice way to check yourself, kind of make sure that you've got the right answers for things. If you know the formula of the compound already, you can also find the percent composition. So as an example of what I mean by this, let's consider water. Good old H2O is going to follow us all the way from Chem 221 through Chem 223. But water, if you remember, we could find the molar mass of water. It's 1 oxygen, which is 16.00 grams per mole, and 2 hydrogens, 2 times 1.01 grams per mole. So the molar mass of water, 18.02 grams per mole. That's to the 100th place, etc., etc. Well, the percent oxygen in water would be the grams of oxygen divided by the total mass times 100%, like we just saw. But in this case, we're going to use the molar mass in the denominator. So 18.02 grams is the mass of 1 mole of water. And in 1 mole of water, as you saw in the formula, there's 1 oxygen, which is 16.00 grams. So 16.00 divided by 18.02, that represents the grams of oxygen divided by the grams of the total mass of water times 100%, 88.79% oxygen. And to find the to find the percent hydrogen, you could do something similar. You would take the mass of the hydrogen. There are 2 hydrogens, which each are 1.01 grams, divided by the total mass times 100, 11.2%, and that's fantastic. However, you would get better sig figs here by going 100% minus the percent oxygen, which is legit too. So instead of 11.2%, you would get 11.21%, which is woohoo! 1 sig fig better. Not a big deal, but either way would be fantastic here, and you get the idea of how this works. So what we've just seen here are 2 methods to find percent by mass. If you know a total mass, like in the last example, you can put that in the bottom, divide, or have in the numerator put whatever mass you're looking for. Or in this case, since we knew the molar mass, we could put that on the bottom and then find the masses of the individual elements, and they should be the same result. This is a question you might see. It says, what is the percent nitrogen in nitrogen monoxide? And MM stands for molar mass. NO is about 30.01 grams per mole. So the nitrogen, there's 1 N in NO. Nitrogen is 14.01 grams per mole. So the percent nitrogen in this case would be 1 nitrogen divided by the molar mass of the whole thing times 100%. Mathematically, that would be 14.01 on top. You would divide it by 30.01 on the bottom, multiplied by 100%. It'll be a little less than 50% because 15 divided by 30 is 50%, and NO is a little less than 14, so it comes out to be 46.68% nitrogen. And there's the better math there on the bottom, but you can kind of estimate. So anyway, no problem. It's just another little trick of the trade if you need to use it. So like we said earlier, the compound's empirical formula is often the first step in determining the identity or the molecular formula of the compound. And you can find the empirical formula from these mass values. If you have the exact masses, you can turn the masses into moles. And then from there, you can take those moles, divide the mole values by the smallest number of moles. That'll give you then whole number ratios. And if necessary, sometimes it is, sometimes it isn't. If you have a fraction, you can multiply the fraction by a whole number to get a whole number ratio of subscripts. So what that means is maybe you'd end up with the first atom being 1 and the second atom being 1.5. Well, that's great, except that you couldn't have an atom which was only 1.5 atoms. Oh, that breaks all the rules of chemistry, which has whole numbers. So you'd multiply both of them by 2. You'd have a 2 to 3 ratio that way instead of a 1 to 1.5 ratio. I'll show examples of how this means here in a second. Let's look at an example here. We have 1.71 grams of carbon and 0.287 grams of hydrogen. Let's find the empirical formula of this compound. Okay, no problem. We're going to turn the grams of C into moles of C. We're going to turn the grams of H into moles of H, and we'll compare the C and the H. So here's the math. 1.71 grams of carbon will divide by 12.01 grams per mole for carbon. You can see there the grams of C cancel out. We've got 0.142 moles of carbon. We're going to do the same thing here for hydrogen. 0.287 grams of hydrogen divided by 1.01 grams per mole. That gets us 0.284 moles of hydrogen. This is kind of a ratio. It's like a ratio, you could think of it as C 0.142, H 0.284, but those are anything but whole numbers, which is what we need in chemistry for formulas. So we'll take those 0.142 and the 0.284, we'll divide it by the smaller number, and 0.142 is smaller than 0.284, so we'll divide both of the moles by 0.142. C comes out to be 1 then, 0.142 divided by 0.142 0.142 is 1, and 0.284 divided by 0.142 in your calculator is a 2 to 1 ratio. So that means we have 1 carbon, 2 hydrogens. Our empirical formula here, CH2. So again, this is not the molecular formula, but this is the first step that usually scientists have to do in order to find that desired molecular formula. So in this particular case, our empirical formula, our smallest whole number ratio of atoms, CH2. Here's another example where we have chlorine and oxygen now instead of carbon and hydrogen. Same thing, let's find the empirical formula. So again, grams to moles, we'll compare the moles, we'll divide the moles by the smaller moles to get the empirical formula. In this case, 5.31 divided by, I believe it's 35.45 grams per mole of chlorine, you end up with 0.150 moles of Cl. Try this on your own, make sure this is cool. And the same thing for oxygen, 8.40 divided by 16.00 grams per mole, you get 0.525 moles of oxygen. So those are the moles now of Cl and oxygen based on those mass values. And again, this is a kind of a formula. It would be Cl 0.150, O 0.525. But wow, is that an ugly formula? You need whole numbers for formulas. So we're going to divide both of those numbers by 0.150. If you do that, Cl 0.150 divided by 0.150 comes out to be Cl1, and oxygen 0.525 divided by 0.150 comes out to be 3.5. So this is better. I mean, we've got whole numbers now for chlorine, but oxygen 3.5, gotta get rid of that, gotta have whole numbers. So we'll multiply both of those through by 2. That means it's going to be not 1 to 3.5, but 2 to 7. So the empirical formula here, Cl2O7. So you can see here that after we divided both of the numbers by the smaller moles, we still ended up with a fraction or a decimal, but 3.5 times 2 is 7. So 2 to 7 is a better empirical formula than 1 to 3.5 empirical formula Cl2O7. Now in Chem 221, you're not going to see crazy ratios. You might see 0.5, all right, and if you multiply 0.5 by 2, you'll get whole numbers. In the real world, though, you might get 3.25, like 3 1/4. And does that mean you have an impurity and you should round down to 3? Or does it mean you should literally then multiply through by 4 or something to get whole numbers? And this is a difficult decision sometimes, but it's one that chemists face. Nothing you can't handle. But again, in our classes, the ratios will be pretty simple. This is a general plan for what we just did and how you go from mass percentages or mass values, I guess I should say, into an empirical formula. So we took the grams of Cl and O, turned them both into moles by dividing by the molar mass. We then compared those moles together, and it turned out it was 3.5 moles of oxygen for every 1 mole of Cl. But we can't leave that stand. We have to have whole numbers, so we multiply them both through by 2 to get 7 to 2 ratio, which means the empirical formula here, Cl2O7. Now, the last examples have had actual masses involved. So we had actual gram amounts of, say, carbon and hydrogen or chlorine and oxygen, and that's cool. But you can do the same kind of process with percent composition values. So in this example now, we're going to have percentages instead of grams, but it's amazingly similar in how you make this happen. First of all, if you have percentages, what I would do is assume you have 100 grams total of your compound. So that way your percentages become grams explicitly. And I'll show you what this means here in a little bit. But once you have the grams of the elements, you can turn grams to moles, divide the mole values by the smaller moles, and if necessary, multiply them all through by an integer to get whole number of subscripts. So in this example, we've got some kind of compound that pops out here. It's 27.29% carbon and 72.71% oxygen. We can can use this information to calculate the empirical formula of this gas. So again, what we're going to do is we're going to take these percentages, assume 100 grams total. That means 27.29 grams of C and 72.71 grams of O. We'll turn the grams into moles. We'll compare them, see if we can find a smallest whole number ratio of atoms. So what I would do is I would assume 100 grams total, so those percentages literally become grams. So 27.29% carbon became 27.29 grams of C, and 72.71% oxygen became 72.71 grams of O. You can use different numbers. Some people like using 1, and that's fine. You'd have 0.2729 grams of C and 0.7271 grams of O, and that's fine. You can use any number you want, but I just use 100 grams because I'm lazy and I don't want to think about it, but you use whatever you want. The next step though, turn the grams into moles. So using my values, I ended up with 2.272 moles of C, 4.544 moles of O. And again, I got those molar masses from the periodic table, no big surprise. We'll then take both of those mole numbers, we'll divide them by the smaller number, which here is 2.272. So if you do that, 2.272 divided by itself is 1. 4.544 divided by 2.272 is almost exactly 2. That means 1 carbon every 2 oxygens. Empirical formula here, CO2. So again, very similar to what we just did, just assume percentages. You want to turn them into grams. I would assume 100 grams, grams to moles, compare the moles, empirical formula, good to go. But the molecular formula is what chemists are really after. And we've seen different ways now to find an empirical formula, but we should talk here a little bit about how to go from an empirical formula to a molecular formula. So again, empirical formula, smallest whole number ratio of atoms. So here's an example of acetic acid, and the compound acetic acid, the Lewis structure is shown in the lower right-hand corner. Now the molecular formula is C2H4O2. What is the empirical formula? And again, you want to take the smallest whole number ratio of atoms. So the ratios there you can see in acetic acid are 2 to 4 to 2, C to H to O. Let's divide all of those numbers by 2. That's going to give an empirical formula of CH2O. And remember, in an empirical formula, smallest whole number ratio of atoms, no fractions. But as long as you understand that, then that's pretty chill. Now, let's look at it from the empirical formula to the molecular formula. CH2O taken twice is C2H4O2. So if we could somehow find that ratio, we could then take that and multiply it by the empirical formula to get the molecular formula. So how the heck do you find that ratio? Well, the ratio that we're looking for is the ratio between the molar mass of the whole compound, i.e. the molecular formula's molar mass, compared to the empirical formula's molar mass. So if we could find the molar mass of the whole compound, then we compared it to the molar mass of the empirical formula, which you can calculate pretty easy, you're always going to get a whole number ratio. And let's call that ratio N, okay? So this is actually not as bad as it might seem. So on the last slide, we saw that CH2O was the empirical formula of acetic acid. Well, in this example, CH2O is also the empirical formula, but we're going to compare it now to a compound which has a molar mass of 180 grams per mole. Now, these numbers come from the mass spectrometer we talked about in Chapter 2. It's a fascinating device, but it allows you to find the grams per mole of the compound. It doesn't say if it has carbon, hydrogen, oxygen, nitrogen, uranium, whatever, but it does tell you the grams per mole. Anyway, we can use this information now to find the molecular formula. And along the way, we need that whole number ratio. We need that value of N. So what we're going to do is we're first going to find the molar mass of the empirical formula. And the empirical formula here, CH2O. So 1 carbon is about 12 grams per mole. Hydrogen is roughly 1 gram per mole, and there's 2 of them. And oxygen is 16 grams per mole. So you can see there I added 12 plus 2 times 1 plus 16, 30 grams per mole. But wait, you're probably going, whoa, Russell, you're using horrible sig figs. You were babbling about how you should always go to the 100th place, blah, blah, blah. Well, in the empirical formula to molecular formula conversion, N will always be a whole number. There's no exceptions to that. So you can use pretty cheesy sig figs because if the N is always going to be a whole number, you can round up, down, whatever you need to get to a whole number, and you'll be good to go. So in this particular type of problem, it is okay to use pretty bad sig figs. So I'm just using 12 for carbon instead of 12.01. I'm using just 1 for hydrogen instead of 1.01, and oxygen is 16. So that's where the 30 grams per mole value came from. Now in this problem, the molar mass of the whole thing is 180 grams per mole, and the empirical formula's molar mass, which is something you need to calculate, 30 grams per mole. So if you find the ratio here between the molar mass of the whole thing, which is 180 grams per mole, you divide it by 30 grams per mole, which is the empirical formula's molar mass. 180 divided by 30 is 6. Now, notice there in this diagram, they're using AMUs instead of grams per mole. AMUs and grams per mole are the same number. You can interchange the units. AMU is per molecule, grams per mole is for a mole, but it's the same number. So you can use grams per mole or AMU. It doesn't slow me or chemists down at all. The important thing is that you found this ratio in this example is 6. So there are 6 empirical formula units in the molecular formula. So if you take the empirical formula, CH2O, and multiply it by 6, you get C6H12O6. The molecular formula, the desired formula of this compound, C6H12O6. So this is how chemists can find the molecular formula of a compound. First, they'll send it away or do it in-house, whatever. They'll find usually elemental percentages, so percent carbon, percent hydrogen, percent oxygen. You can then assume 100 grams, convert the grams to moles, etc., to find the empirical formula. And then in a separate experiment, and this is what's cool, they can find the molar mass of the whole compound. And if you compare the molar mass of the whole compound to the molar mass of the empirical formula, you will always get a whole number. You multiply the empirical formula by that, molecular formula is yours. And it sure beats the heck out of tasting it or something like that, which is deadly and dangerous and silly, but kind of fun to think about. This is the way that chemists find formulas. Here's an example of a compound called glyceraldehyde. It also has an empirical formula of CH2O. So see, there's lots of these compounds with the same empirical formula in organic chemistry. But anyway, the molar mass of the whole compound, 90.08 grams per mole. What is the molecular formula? Well, 90.08 grams per mole goes in the numerator, the top. And in the bottom, you want the empirical formula's molar mass. And this is when you can be really cheesy with your sig figs. It's terrible. I have to get excited by this. But anyway, carbon is about 12 grams per mole. Hydrogen is about 1 gram per mole, and there's 2 of them. Oxygen is 16 grams per mole. Add 12 plus 2 times 1 plus 16. That's about 30 grams per mole. And 90.08 divided by 30 is about 3. Remember, these ratios will always be whole numbers, so about 3 means 3. So 3 times CH2O would be C3H6O3. So you can see there's my rough molar mass, about 30 grams per mole. I did not use explicit sig figs because it's not necessary. The ratio of the molar mass of the entire compound to the empirical formula, always a whole number. This ratio is 3. We'll take our empirical formula 3 times to get the molecular formula, C3H6O3. Cool. Another method that's used to find a formula, especially in organic chemistry, is called combustion. And in combustion, which we'll look at more in the next section, Chapter 7, Part 1, you're taking a hydrocarbon, which is a compound with only carbon and hydrogen, at least usually. You burn it in O2, and you end up with CO2 and water. And CO2 and water, if you collect it, you can then back calculate how many carbon moles you have, how many hydrogen moles you have to find the formula. But you have to remember that all the carbon ends up as CO2 and all of the hydrogen ends up as water. So this is kind of a cool process. It's mostly used in organic chemistry, but you can see how maybe this could have some cool implications for what we're talking about here.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
The CO2 and the water are collected with different systems. In this particular example, magnesium perchlorate is a good compound for absorbing water. So if you measure that little blue box, if you will, before and after, then the grams difference will be the grams of water absorbed. And for different reasons, sodium hydroxide is good at absorbing CO2. So again, the mass of that purple box now, before and after, the difference will be the grams of CO2. So it's not too difficult of a kind of a system to use. We used to have one of these when I went to graduate school, and we could collect these kind of things for hydrocarbons. It really only works for carbon and hydrogen systems, but again, in organic chemistry, these are so common. That's why we're talking about it here. They can be really useful. This is an example of how this works. Hydrocarbons are often liquid, at least some of them are anyway. As an example of this, if you drive in a gas-powered car, the gasoline is usually octane. Octane is a liquid, as you know, if you've ever filled up your car. It's usually a puddle of liquid. Now, not all of these are liquids, but a lot of them are. So in this case, we're taking 0.115 grams of some random hydrocarbon. I'm going to call the hydrocarbon CXHY. So that tells you that your hydrocarbon has only carbon and hydrogen in it, and our goal here is to find out what X and Y are. But we're going to burn it in O2, and at the end we collected 0.253 grams of CO2 and 0.1035 grams of water. Now we also sent the same hydrocarbon off for a molar mass analysis, and we found it was 84.16 grams per mole. We can use this information to first find the empirical formula of our hydrocarbon, and then we'll find the molecular formula. In this process, our compound, our 0.115 grams, had only carbon and hydrogen in it. So when we burned it, we added O2. All the carbon ended up as CO2, and all the hydrogen ended up as water. Now, carbon dioxide has one carbon in it. So for every CO2 molecule that was created, we had 1 mole of carbon, and that came from the hydrocarbon CXHY. Now, for water, since the formula is H2O, that means there are 2 hydrogens for every water created. So when we find the moles of hydrogen, we're going to have to multiply the water by 2 because water has 2 hydrogens, and I'll show you what this means here in a little bit. So for CO2 and carbon, it's 1-to-1, but for water and hydrogen, there's 2 hydrogens per water, and you'll see that here in a little bit. Let's first of all, we're going to take that carbon and we're going to analyze it. There's 0.253 grams of CO2. We'll turn it into moles, and then every mole of CO2 equals the moles of carbon in our original hydrocarbon. So 0.253 grams divided by the molar mass of CO2, which is about 44.01 grams per mole, that gives you 0.575 times 10 to the minus 3 moles. Make sure you can do that calculation on your own, okay? Find the molar mass of carbon dioxide, 0.253 grams divided by the molar mass, you should get 5.75 times 10 to the minus 3. And for every mole of CO2, there's an equal number of moles of carbon. So that means our hydrocarbon had 5.75 times 10 to the minus 3 moles of carbon in it. We're now going to do the same thing for water. We're going to turn 0.1035 grams of water into moles by dividing by the molar mass of water. I'm hoping this is sounding more and more familiar to you, but it's 18.02 grams per mole. So turn the grams of water into moles of water, and now multiply moles of water by 2 to get moles of hydrogen, because water is H2O. So if we want to find moles of hydrogen specifically, we'll multiply it by 2. So 0.1035 grams divided by the molar mass of water, 18.02, you get 5.744 times 10 to the minus 3 moles. But we'll multiply that through by 2 because there are 2 hydrogens in water. It's H2O. So moles of water times 2 will give you moles of hydrogen. Now we've got the moles of C from before. We've got the moles of hydrogen now. This is a rough formula. It's C 5.75 10 to the minus 3, H 1.149 times 10 to the minus 2. But man, is that an ugly formula. All right, chemists love whole numbers for atoms, obviously. So in the next part now, we're going to divide both sides by the smaller moles like we did earlier. 5.75 times 10 to the minus 3 is smaller than a 10 to the minus 2 number. So we'll divide by the 5.75 10 to the minus 3. What this looks like when you do the math, 1.149 10 to the minus 2 divided by 5.7 10 to the minus 3, that ratio comes out to be almost exactly 2. Now remember that 5.75 10 to the minus 3 divided by itself is just 1. That's the moles of carbon. And with this other part now we're seeing is that this other ratio of hydrogen to carbon is 2 to 1. So what that means is you have 1 carbon for every 2 hydrogens. Your empirical formula, CH2. Woohoo! And I know it's kind of exciting. Now, in the lower right-hand corner is a meme. It says, what's the chemical formula for nitrogen monoxide? And the student goes, no. And the teacher goes, good, sit down. Because nitrogen monoxide is NO, okay? And the student accidentally said the right formula, even though they didn't know it. So that's why the poor student there is a little bewildered. Anyway, at this point, you can see the formulas are all over the place. Nothing you can't do. Just remember grams CO2 to moles of CO2 equals moles of C. Grams of water to moles of water times 2 gives you moles of hydrogen. We compared the two, smaller number on the bottom, bigger number on the top. In this case, it's 2 to 1, CH2. Don't feel like that, student. You got this, okay? But we're not done, all right? Because CH2 is the empirical formula, and what we want to do now is find the molecular formula. Now, another piece of information in this problem was that the molar mass of the whole thing, 84.16. So what we're trying to do now is compare that 84.16 to the empirical formula's molar mass. And we're going to get a value, an integer, which is always going to be a whole number. So since we found that the empirical formula is CH2, we can add up 1 carbon and 2 hydrogens to find the molar mass of the empirical formula. Now, if you do that with lots of sig figs, that would be 12.01 for the carbon, 2 times 1.01 for the hydrogen, 14.03 grams per mole. Now, really, you just need to do it rough here. So 14 would be an acceptable value by all means. The next step, you want to compare the molar mass of the whole thing, 84.16, to the molar mass of the empirical formula. You will always get a whole number. In this case, that ratio comes out to be almost exactly 6. So 6 times the empirical formula is going to give you the molecular formula. We'll take CH2 6 times. So that means there are 6 carbons and 6 times 2, 12 hydrogens. Our empirical formula here, C6H12. So this is how you can find the molecular formula of a hydrocarbon. It's pretty cool, pretty chill, nothing you can't handle. It's a little weird at first. I completely dig that, but you got this. Some compounds have the same percentages, the same empirical formula, but their molecular formula is different. And so this is why we're making such a big deal of it. Like if the compounds were made and there was only one possible answer, we would be good to go. Now, one example of this is nitrogen dioxide compared to dinitrogen tetraoxide, NO2 to N2O4. And NO2 is a brown paramagnetic gas. It's very, very deadly, and it's something you don't want to mess around with. On the screen down there, the picture in the lower right, the brown container is NO2, and that's really nasty stuff. N2O4 is another compound. It's a colorless gas. It's diamagnetic. And I hate to say I would want to breathe it, but if you have to take a whiff of something, N2O4 would be much safer. All right, it's not as reactive. Diamagnetic things are generally not as reactive as paramagnetic things. I don't want you to breathe either one of them, but if you had to take one, N2O4 would be the better one. So this is why it's so important to find the molecular formula. Compounds might have the same percentages, the same empirical formula, but if you don't know that molecular formula, it can make a big difference. And in organic chemistry, there's tons of examples of this, and some of them are better for you as a person than others, or some of them will react in a one way that other ones won't. So this is why chemists make a big deal of both empirical formula and molecular formula. This is an example I'd like you to try on your own. I'm giving you all the answers so you can find out if you've got this down or not. In this example, we've got a boron hydrogen compound. It's 81.10% boron, and the molar mass of the whole thing, 53.3 grams per mole. What's the empirical formula? What's the molecular formula? Well, first of all, you're only given one percentage, but if there's only boron and hydrogen, then 100% minus the boron will give you the hydrogen. So that's how you can find the percent hydrogen. And if you assume 100 grams, you can turn those percentages into grams. Take the grams divided by the molar mass of boron and the molar mass of hydrogen. You should end up with 7.502 moles of B and 18.75 moles of H. And you can take those moles to find the empirical formula. The best empirical formula here comes out to be B2H5. You can compare the molar mass of the empirical formula to the molar mass of the whole compound, 53.3. The ratio comes out to be 2, so twice the empirical formula, B2H5 twice, B4H10. Make sure you can do this, okay? We'll do some of this throughout the whole year from Chem 221 all the way to Chem 223. So as long as you can do this problem, you should be in good shape and be ready to rock and roll. In section 6.3, we're going to look at molarity, types of mixtures, and this is another super important part of chemistry. A lot of the labs that we've done so far have used solutions where you have something, a solute, the exciting part, dissolved usually in water, the solvent. And there's a lot of really cool reactions that can happen if you have a solution relative to the pure substances. Now, earlier we talked about mixtures, and most of the time in the wild, if you go out in the woods or something, you'll find mixtures of things. You don't usually find pure substances. And when chemists think about it, they can be heterogeneous mixtures, which means you have more than one phase visible, or homogeneous mixtures. Now, heterogeneous mixtures will be things like rocks in water, or different kinds of rocks together. All those kind of things. You can actually see them at this different phases inside there. In our day-to-day world up there in the upper right-hand corner, like a piece of pizza would be a heterogeneous mixture. You've got the crust, you've got the cheese. In that example, you've got looks like little peppers on there or whatever. Lots of different pieces, so that would be heterogeneous mixtures. No problem. Now, homogeneous mixtures are a little bit more cautious, that you have to be careful around them, because homogeneous mixtures will look like just one phase. So as an example of that, let's say your friend decides to pull a trick on you, and he or she puts a lot of salt, table sodium chloride, in your water. All right, mixes it up. It looks just like water, but goodness, you take a drink of salt water and you know it's not regular water. It's got kind of a weird, funky taste to it. Salt water freaks me out. Anyway, that's a personal story. You don't have to worry about that. So homogeneous mixtures, they'll look like just one substance, but they're usually going to be more than one. And even though in salt water, that's a bad trick to play on someone, in the laboratory, this can be really useful, because a lot of times solutions will have a lot of different characteristics than the individual substances will. And we'll talk about why this is as we go through the class. A solution is a homogeneous mixture. It's a single phase. So you're going to put two things together and they'll end up having one phase. And a good solution will have uniform composition, which means they've been mixed well. So the top will have just as much of the substances as the bottom will, all right? And if that's the case, then you can describe the solution through what's called a concentration. Now, a solution will have a solvent and a solute in it. Solvent is the component whose physical state is preserved. So, for example, most of our solutions will look like water, all right? Water is the phase that's preserved. And your friend earlier took table salt and dissolved it in water. Well, table salt was a solid. You're putting it with liquid water, and at the end, the solution looks like water. So solvent is usually just the same phase, if you will, as one of the components, which is usually water. And most of Chem 221 through Chem 223, water will be the solvent, but you could have octane, olive oil, whatever. Solute, on the other hand, is the more exciting part of your solution. When you say salt solution, you're implying that the salt has an active part, and it does. Like you taste salt water and it's funky, all right? So solute is the more exciting part. You can have a sugar solution. You can have an acid solution. Those are the exciting parts, the parts that make the solution different from the pure solvent. If your solution has water as a solvent, a lot of times it'll be called aqueous. And aqueous, sometimes you'll see a little AQ next to it in brackets. We'll talk about this more in the next chapter, but I'm just getting you ready. If you see AQ, it means that you have the substance dissolved in water. So NaCl, table salt, in its pure form would be NaCl as a solid. But NaCl in water, you would write NaCl with an AQ next to it to show the other chemists that this is what you have. You have a salt solution, not sodium chloride in its pure state. The most common way to describe the concentration of your solution is through something called molarity. And molarity, which gets the capital M, is the king of all the concentration units. And we'll look at other concentration units, but molarity is the one we'll use most of all. So molarity, big M, is the moles of solute, the exciting thing in your solution, divided by the liters of solution. So if you see a number that's like 3.6 M, and by the way, M has to be capitalized, don't use little m, that would mean 3.6 molarity, or 3.6 moles of whatever you're looking at, the solute, per liter of solution. And it's a really common way to describe solutions. It's so common that a lot of times people will just say concentration when it's molarity. Now, technically, they're different. All right, molarity is only one of several types of concentrations, but it's so common, this is why it happens. In the little picture in the lower right, the solute in that case is that blue compound, probably a copper 2 chloride. Anyway, and they're placing it in water, the solvent, to make the blue solution. So that solution would have the blue compound as the solute, water would be the solvent, and the solution, of course, is what's made.
To prepare a solution of known concentration, we must first weigh the solute. We need an accurate volumetric flask designed to hold 250 milliliters. We first add the solute to the empty flask. The flask is filled about halfway with water and mixed to dissolve the solute. We add water in stages. Combining all the solvent with the undissolved solute in one step can lead to inaccurate measurements. We mix again. The solution is prepared.
So let's pretend that we want to make a nickel 2 chloride solution, all right, in water. And nickel 2 chloride often comes as nickel 2 chloride hexahydrate, NiCl2.6H2O. So when you measure out solid, it's not just Ni and Cl2, the waters are actually part of it as well. So let's pretend in this example that we're taking 5.00 grams and we're placing it in enough water to make 200 250 milliliters of solution. We can use this information to calculate the molarity. Now, in that video, they use what's called a volumetric flask. Volumetric flasks have one line on them, and if you fill the liquid up to that line, so the bottom of the meniscus, the bottom of that dip in water, touches the line, then you have, in this case, exactly 250 milliliters. So you can see the little dot right there. That's implying that you have 3 sig figs for your volume term. Anyway, to find the molarity then of this solution, we need to take our grams of solute, the NiCl2.6H2O, and turn them into moles. So you need to find the molar mass of that NiCl2.6H2O and make sure you add on the 6 H2Os because that's part of the solid. And then in the denominator, the bottom of the calculation, will have liters of solution. Now there are 1,000 milliliters in a liter. You're going to use that a lot in this section, so that's a cool thing to know. So we'll take 250 milliliters, divide by 1,000 to find the liters. So if you do all of this, first of all, you need the molar mass, like I said, of NiCl2.6H2O. And if you add up all of those, it comes out to be 237.7 grams per mole. So 5 grams divided by the molar mass, the grams cancel out. You've got 0.0210 moles of nickel 2 chloride. There are 1,000 milliliters per liter, so 250 divided by 1,000 is 0.250 liters. So the moles of solute, 0.0210, divided by liters, 0.0841 molar. So that means there's 0.0841 moles of nickel 2 chloride in a liter of solution. You don't have to worry about the 6 waters once it's in water. They just kind of float off with the other waters. It's the nickel 2 chloride which is most exciting. However, if you want to be complete, it is a nickel 2 chloride hexahydrate solution. Not as exciting, but anyway, sometimes you'll see molarities listed with square brackets like that. So if you saw NiCl2.6H2O equals 0.0841 molar, that's saying that the concentration of the nickel 2 chloride is 0.0841 molar. That's what that means. Sometimes you'll need 250 milliliters of a 0.0500 molar solution, i.e. you'll need such a volume of a certain concentration, and you want to know how many grams to add to your liquid. And this is another very common example of a problem that chemists will run into. So in this problem, we're using oxalic acid, H2C2O4, and you can buy this from at the store, Home Depot, whatever. It's H2C2O4, and we need 250 milliliters of a 0.0500 molar solution. Well, we can absolutely figure this out. Molarity, big M, is moles per liter. So that big M, you can substitute in moles over volume if you want. And it's moles per liter. So if you turn your 250 milliliters into liters, moles divided by liters, the molarity times the liters, 0.250 liters, will give you the moles of solute that you need. And in this example, it'll be moles of oxalic acid. So if you do that, 0.0500 moles per liter is what big M stands for, and you multiply by the liters of solution, 0.250 liters, you're going to end up with 0.0125 moles of solute, 0.0125 moles of oxalic acid. Once you have the moles of the solute, you can then use the molar mass of oxalic acid. So you'll need to find the molar mass of H2C2O4. It comes out to be 90.00 grams per mole. Multiply that by the moles you need, and you calculate 1.13 grams. So what this number says is that if you measure out 1.13 grams of oxalic acid and dissolve it in 250 milliliters of solution, you're going to end up with a 0.0500 molar solution, which is kind of cool. So in the last example, you had so many grams and so much volume, and you calculated the molarity. In this example, you need so much volume of a certain molarity, and you calculated how many grams you needed in order to make that. And both of these methods are very, very common in chemistry. So when you prepare a solution, there are two methods that are used often in chemistry. And one way is you measure out so many grams of a solid and dissolve it in so much volume. Or if you want, you could find the grams that you need based on the volume and the molarity of your thing. But another method that's very, very common is to dilute a solution.
To prepare our solution using the dilution method, we first obtain 2 milliliters of stock solution with a pipette. Filling the pipette with stock solution to the mark on the pipette ensures that we have 2 milliliters of this solution. We add the 2 milliliters of more concentrated solution to the 500 milliliter volumetric flask, touching the side of the flask with the pipette. We add water to the mark on the flask. After mixing thoroughly, we have exactly 500 milliliters of a solution with a concentration of 1.60 times 10 to the minus 4 moles per liter.
In this video, they took a concentrated solution, and on the left there, you can see that solution is a pretty deep orange color. And they took a little bit of it out, added a bunch of water, and ended up with a new solution. And the new solution you can see is much less intense in color. It's a yellow, but it's not nearly as intense as the orange. So this is an example of when a solution has been diluted. You end up with a less concentrated solution once you take a little bit of a concentrated solution out and add water to it. So in the lower right-hand corner, there are two examples of a copper 2 nitrate solution. On the left, if you look carefully, that is a more intense blue, and on the right, it's less intense. So the less intense blue came from taking the concentrated version and adding water to it. So water will make your solution less intense looking color. That's one visual way you can see. But as long as you know the concentrations, you can calculate what the values are and figure it out from there. Now, a lot of our acids and bases are delivered to us in very concentrated forms. And they're so concentrated that if we were to use them in the lab, it would eat through a lot of our equipment. Very, very powerful chemicals. So what we'll do in the stockroom, or what you could do yourself, is you take a little bit of the concentrated solution out, add some water to it carefully, and then you make a more manageable and easier to handle solution, which is less concentrated. So this is actually very common in the chemistry lab. When you're going to dilute an equation, there's something called the dilution equation, and it has different forms. The one that our textbook uses mostly is C1V1 equals C2V2, where C is a concentration, a molarity, and V is a volume. So you can see that 1s represent the initial values and 2s would be the final values. Now, sometimes you'll see it MIVI equals MFVF, where I is initial and F is final, and instead of C for concentration, they'll use M for molarity, but either way is fantastic. So I don't care which version you use. Let's see how either version will work. So in the example there, we've got 0.850 liters of a 5 molar solution of this copper 2 nitrate, and we're diluting it to a volume of 1.80 liters. So the question is, what's the new molarity? So 0.850 liters is V1, 5.00 M is C1, and then 1.80 liters would be V2. You essentially want to solve for C2. So C2 would be C1 times V1 over V2. It's pretty chill. So in this case, 5.00 molar times 0.850 liters, that's C1 times V1. We'll divide it by V2, 1.80 liters, 2.36 M would be the final concentration, C2. So our new solution is now less concentrated. It was 5.00 molar, and now it's 2.36 molar. And in order to do this, in order to get the 1.80 liters, we added 0.950 liters of water. Notice that this came from initial volume to final volume. There was already 0.850 liters there, so we added 0.950 liters to make the volume 1.80 liters. Good to go. Again, this is somewhat common when it comes to chemistry, so that's why we're tackling it. Here's an example where a student took a 3.00 molar HCl solution, 20 milliliters of it, and they accidentally, or perhaps intentionally, hard to say, added it to 100 milliliters of water. So the total volume, which is, by the way, what you want in V2, 120 milliliters. So the question is, what's the new concentration of the HCl? So in this case, V1 is 20.0 milliliters. C1, the initial concentration, 3.00 m. And final volume, V2, would be 120 milliliters. You want to solve for C2 like we did in the last one. When you do that, it comes out to be 0.500 moles per liter. And notice you can use milliliters over milliliters, like in this example, or in the previous example, we had liters over liters. As long as your volume units are the same, you can use anything you want. You could use nanoliters over nanoliters. You just want to make sure that those volume units cancel. That's the important punchline of all this stuff. Here's another example that's kind of important. Let's say that we have 50 milliliters of a 3.0 molar sodium hydroxide solution, but we want only 0.50 molar sodium hydroxide. So maybe this is the concentration we need for a reaction, something like that. Well, if we want the concentration, the molarity, to decrease, i.e. go from 3.0 molar to 0.50 molar, we're going to have to add some water. We want to dilute the solution, all right? So we're going to end up with a bigger volume at the end than we started with. And in this problem, we're not adding any more sodium hydroxide, all right? We're just adding water to it. So the number of moles, like those little yellow spots in that picture on the lower right, will be the same on the left and the right. We just have more water. But how much water do you add? Like how much water should you add to the 50 milliliters of 3.0 molar sodium hydroxide to make the final solution 0.50 molar? And that's a kind of question that you'll run into sometimes in these problems. Well, the moles don't change. So what I would probably do here is I would take 3.0 moles per liter and I would multiply it by the volume that we started with, 0.0500 liters. So that means we have 0.15 moles of sodium hydroxide in our initial solution. All right, no problem. And again, we're not changing that number. Now, what we want is 0.50 moles per liter sodium hydroxide. So what you can do here then, the final solution is also going to have 0.15 moles sodium hydroxide. And since big M is moles per liter, and we want 0.50 moles per liter, let's take the 0.15 and divide by 0.50 moles per liter. So you can see there moles on the top and moles on the bottom will cancel. We'll be left with liters, and the calculation then comes out to be 0.30 liters or 300 milliliters. But that's the volume of the final solution, and we already had 50 milliliters of solution. So if the final volume needs to be 300 and we already had 50, that means we're going to add 250 milliliters of water to the 3.0 molar sodium hydroxide to the 50 milliliters, and that'll make 300 milliliters of 0.50 molar sodium hydroxide. So this is how people can calculate then how much volume of water you need to add to dilute your solution to a less concentrated value. And it's not that hard. Just remember the moles are the same. All right, the moles have not changed. And when you finally get a final answer, remember you've already got some volume already present, and you need to take that out before you start adding water. In this question, we have 60 milliliters of 0.25 molar HCl, and we place all of it in a 500 milliliter flask and add water to get to the final point. So our final volume is 500 milliliters. And the question is, what's the concentration of the HCl? Well, again, I would use C1V1 equals C2V2. The initial volume is 60 milliliters, the initial concentration 0.25 moles per liter, and the final volume is 500 milliliters. So let's solve for C2. C2 then would be 60 times 0.25 divided by 500. Again, notice that as long as the volume units are the same thing, you don't have to change to liters unless you want to. Final concentration, 0.030 moles per liter. So in this example, we're diluting to 500 milliliters. We already had 60 milliliters, so we would add then 440 milliliters of water to make the 500 milliliter flask filled up. Good to go. There are other kinds of solution concentrations. They're not as common as molarity, but it is worth talking about them. A lot of times with environmental studies, like figuring out contaminants, pollution, stuff like that in the water and in our air, they will use what's called a parts per million or a parts per billion. And mass percentages are also used sometimes, as well as volume percentages. So let's just briefly look at these and see how they work. A mass percentage is the first one we're going to look at. It's usually mass percent of some kind of solute. So it'll be like we saw earlier, the mass of what you're looking at divided by the mass of the whole thing times 100%. Now, a volume percentage is similar, except they're going to use like milliliters or liters or quarts or whatever. So it'll be the volume of what you're looking at divided by the volume of the whole solution times 100%. Now, mass percentages are more common than volume percentages, but you will see some volumes, just letting you know. In this example, we're adding 25 grams of sodium chloride to 55 grams of KCl. So it's a mixture, a solid mixture here of NaCl and KCl. And the question is, what's the mass percentage of NaCl in the mixture? No problem. So in the numerator, you'd have the grams of what you're looking at, sodium chloride, the solute, if you will. We'll divide it by the total mass on the bottom. So 25 plus 55 is what we'll put on the bottom. I think it comes out to be 80. And we'll multiply that fraction, if you will, by 100%. So if you do that, 25 grams of sodium chloride in the top divided by 25 plus 55, I believe that's 80, multiply that by 100%, 31.3% sodium chloride in this mixture. So if you see one of those, that's what's useful. These do have some uses for them. We'll look at these more in Chem 222, but remember, it's grams of what you're looking at divided by grams total times 100%. This is for mass, which is grams. Here's another example. This is an example of some spinal fluid that was taken out of someone. Oh, freaky. Anyway, their spinal fluid has 3.75 milligrams of glucose. They want to know the mass percent of glucose. All right, no problem. Remember that these mass percentages, you have to use grams over grams or milligrams over milligrams. So make sure everything is in the same kind of unit. So in this example, there's 1,000 milligrams in a gram. So let's first convert milligrams to grams by dividing by 1,000. We'll then divide by the total mass, which in this case is 5 grams of spinal fluid times 100%. Mass percent of glucose here, 0.075%. So this is again how they do mass percentages. Kind of freaky to think about spinal fluids and stuff, but hey, it works and it's great, and I'm so glad they can do it. Medicine is pretty cool. This is an example of a volume percentage, which again is not used as much, but I wanted to show you an example of how this works. In a radiator, people will usually have water, but they will put either ethylene glycol or propylene glycol to make it not freeze as easily when it comes to the winter. So let's say that this car person, they took 50 milliliters of ethylene glycol and they added it to 120 milliliters of water. So 120 plus 50 is 170 milliliters total, and they want to know the volume percentage of the ethylene glycol. No problem. So again, in the numerator, the volume in this case of what you're looking at, 50 milliliters, divided by the total volume, which in this case is 170 milliliters of water plus ethylene glycol, multiply it by 100%. So 50 divided by 170 times 100% is what you'd throw in your calculator, 29.4% ethylene glycol in this mixture. So this is a volume percentage. Again, these aren't used very often, but if you do see it, just realize it's based on volume. And you could use liters over liters. You could use microliters over microliters. Just make sure that your volume units are the same kind of volume and you'll be good to go. Part per million and all the parts per units, as we'll talk about, are used a lot of times when you're talking about things in the environment. Now, in the environment, like if you went down to the Sandy River and took a sample, the amounts of some of these these chemicals are going to be really, really small, but they can be relevant. So for example, if you have too high of parts per million arsenic in your water, it can make a big difference on your health, stuff like that. If you're dealing with parts per million, which is a lot of times abbreviated ppm, often water will be the solution, and they just assume that the density of your solution is 1 gram per milliliter of water. So this is an abbreviation that's used, and because the amount of solute is so small, it's not really a big deal. So let's see an example of how this works. First of all, if you have a parts per million, you would usually take the grams of solute, the grams of what you're looking at, divide it by the grams total of solution, and you'll multiply by 1,000,000. 10 to the 6 is 1,000,000. So again, the numbers come out to be small, and you're still multiplying by 1,000,000. So that just shows you've got lots and lots of solvent relative to solute, or solution relative to solute. But you don't even have to have parts per million. You can have parts per billion. Now, a part per billion, a billion is 10 to the 9th. So mass of solute divided by mass of solution times a billion, 10 to the 9th, is how you get a parts per billion number. If you saw parts per thousand, that would be 10 to the 3rd, because 1,000 is 10 to the 3rd. So you can adjust your thing accordingly to get numbers which kind of make sense, if you will. But we'll use parts per million here mostly, but you could have parts per billion, parts per thousand, parts per trillion would be 10 to the 12th. Whatever you need, it can be figured out. Here's an example. We're looking at some kind of pollutant in groundwater. The pollutant is 5.0 milligrams, and it's in 100 grams total of your groundwater. We can express this concentration as a parts per million. Now, what we're going to do here is we first need to turn the 5 milligrams into grams, because we need grams over grams, and we have 100 grams total. So if you do all of this, here's 5 milligrams divided by 1,000. That'll turn your pollutant into grams. We'll divide it by 100 grams total, multiply by 10 to the 6, which is 1,000,000. This comes out to be 50 parts per million. So again, not a very big amount, but it could be enough to make differences in terms of people's health and stuff like that. Here's another example you might see. Here's a water source. It has an arsenic level of 75 parts per million. And the question is, how many grams of arsenic are in exactly 1 liter of water? Now, in these kind of problems, you just assume that the density is exactly 1 gram per milliliter. All right. That's kind of cheesy, as we've seen, but it works for these kind of problems because the values are pretty low. So if you have 1 liter of water and you grab 1 gram per milliliter, first you'd go to milliliters. That would be 1,000 milliliters, and 1,000 milliliters, 1 gram per milliliter, would be 1,000 grams of water. So 75 parts per million would be 75 grams of arsenic in 1,000,000 grams of water. So 75 grams per million grams, and if you convert it all over from a liter, you're going to see that there's 0.075 grams of arsenic. So your 1 liter of water has only 0.075 grams of arsenic, which doesn't seem too threatening, but arsenic can be kind of funky. So that's why they use these kind of values then to figure it out. You could go to molarity and stuff like that from there. You could turn grams of arsenic into moles of arsenic, divide it by a liter, etc. However, most of the time, parts per million works great for these kind of analyses. So one final example to finish out this chapter. I'd like to do kind of a combined problem here, where we're going to take some data, we're going to find the empirical formula, the molecular formula, and the molarity of the solution. So let's say that you're digging around somewhere and you find a solution in a cabinet that hasn't been used for a long time and the label's fallen off or something like that. So you send away a sample for analysis, and you have a 5 milliliter sample that you evaporate the water and you collect 98.5 milligrams of some unknown compound. And if you send the milligrams away to be analyzed, you find that it's 49.9% oxygen, 37.5% carbon, 12.6% hydrogen, and you have a molar mass of 32.04 grams per mole. Well, from all this information, you can find the empirical formula, the molecular formula, and the molarity of your solution. So we'll kind of figure out some stuff from the first part of chapter 6, where we found empirical and molecular formulas, and then we'll also be able to find the molarity from all of this as well. So it's kind of a cool problem on that level. So what we're going to do is we're first going to assume we have 100 grams total of the compound. We'll turn all those percentages into grams, grams to moles, and we'll find the empirical formula. And once we have the empirical formula, we'll compare that to the molar mass of the compound to find the molecular formula. And finally, we'll use all this information to find the molarity, the moles per liter of the solution. So kind of cool. So the first thing I would do, assume you have 100 grams total. So all of those percentages become grams. We'll have 49.9 grams of O, 37.5 grams of carbon, etc. We'll turn the grams into moles. We'll compare the moles. The smaller moles goes on the bottom of all three of them. We'll use that to find the empirical formula. So 49.0 grams of oxygen divided by the molar mass of oxygen gets 3.06 moles of O. Do the same thing for carbon, 3.12 moles of carbon, and same thing for hydrogen, 12.5 moles of hydrogen. Now, all of those numbers, 3.06 is the smallest, so we're going to divide all of those numbers by 3.06. That comes almost exactly to 1 carbon for every 4 hydrogens and 1 oxygens. So the empirical formula, CH4O. All right, 4.08 is close enough to 4. I would feel confident in calling that. It'll also make sense here based on the molar mass we're going to have a little bit. But you can see again, all those numbers, divide them by the smallest moles, divide them by 3.06, and you're good to go. So the empirical formula, CH4O. But this isn't the molecular formula. So now what we're going to do is we're going to compare the molar mass of the whole thing, 32.04, to the empirical formula's molar mass. So we're going to take 1 carbon, 4 hydrogens, and 1 oxygen and compare it to the 32 number. And if you do that, and again, this is the part you can use cheesy sig figs if you like. I used a little bit better sig figs here, and I got 32.05 grams per mole for the empirical formula. Well, the molar mass of the whole thing was 32.04, so 32.04 divided by 32.05 is almost exactly 1. So this means that the molecular formula is the empirical formula taken one time, or CH4O is the molecular formula of the compound. So in this example, the empirical formula and the molecular formula are the same, and this does happen. So for example, water is H2O. The empirical formula and the molecular formula are the same. For this compound, CH4O is the same empirical and molecular formula compound as well. Last thing to do, we're going to find the molarity. We know we have 98.5 milligrams in 5 milliliters of volume, and it has a molar mass of 32.04. All right, so we can use all this information to find moles on the numerator and volume in liters in the denominator. So 98.5 milligrams, we'll turn it into grams first. So there's 1,000 milligrams per gram. We'll divide it by the molar mass, 32.04 grams per mole. 3.07 times 10 to the minus 3 moles of whatever compound this is. And we'll then divide it by the liters of solution. So 5 milliliters turned into liters, 0.005 liters. Moles over liters will lead us to molarity. That comes out to be 0.614 molar. So this solution in the cabinet, 0.614 moles per liter. So this compound works out to be nicely methanol. Now, technically, methanol is a liquid. We won't go there, but anyway, we'll assume that they were able to make a solid. But anyway, you get the idea. You can use all this information to find empirical formula, molecular formula, and then find the molarity. Pretty cool. You too can be a cool chemist. Woohoo! That's it for chapter 6. Thank you for being here. In this section, we looked at empirical formulas, molecular formulas, and molarity. Those are the big things and stuff, definitely, that will help us as we go all the way through the remaining chapters, not just of Chem 221, but also Chem 222 and Chem 223. Thank you for listening to me and being here. I hope this has helped, and I hope you have a wonderful day.